Okay, let's take a look at a little bit of a different one. Now, this is a second order. We've been through a couple of first order systems and seen how they perform. Now let's look at a second order system and see how it works. So let's start off with a transfer function. Let's imagine a g of s. Let's go 30, s plus 10, and then s squared plus 3s plus 50. Okay. Now, look at this, and we factor it, and it's factored into a second order system. We can't, there's no factoring this, and so we look at it, and we could also rewrite this as, let me rewrite this as 7 point something squared would be 50. 7 squared would be 49, so let's call it 7 point something, which will be good for our analysis here. And so we've got this the system. So let's first start with a DC gain, just like we have been, and DC gain is going to be 30 times 10 divided by 50. I'm going to go back to 50 on this. And we work that out, and it ends up to be 6. And so the DC gain in dB is going to be 20 times the log of 6, which ends up being 15.56 dB. Okay. All right, so 10 to 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. And so we're at omega equal 1. Let's go 0, 20, 40, minus 20, minus 40. And at omega equal 1, we're going to go to 15, which is about up in here. Right there. And we have no free s's, so we're going to start horizontal. If we had free s in the numerator, we would start with a positive 20 dB per decade slope. If we had a free s in the denominator, free s in the numerator, positive 20 dB. Do free s in the denominator, negative 20 dB per decade slope. No free s's is just horizontal, 0 slope. Okay, so we're going to start there like that. So now we're started, and we're going to go to where we find the first pole or 0. Now actually, our first pole occurs here, okay, at the 7 point something. Okay, if we look back at our rules here, what we see is we're looking at this case. Okay, we've got a s squared 2 zeta omega n. You guys all remember this, plus omega n squared. Our break frequency is going to be omega n, so we're going to take the square root of that, which is why I did that. And in this case, we're going to break, have a change in slope of minus 40 dB, and that's because we've got 2 poles. And so each pole contributes a minus 20 dB per decade, so 2 poles is going to be a minus 40 dB per decade. Now, if they were zeros, we would just apply that same kind of thing in the other direction. It would still happen at the omega n. But in this case, it would be 40 dB per decade, so it would be a positive slope. Now, we also can look at the phase while we're here, and because we've got minus 40 dB per decade, we're going to be at a minus 80 degrees, a minus 180 degrees, and a positive 180 degrees for when we have the contribution after the break. Okay, so let's get back to this, and what we see then is we're at 7 something, which is about, let's see, 2, 3, 4, 5, 6, 7, somewhere around in here. So at this point, we're going to break minus 40 dB per decade. So I'm going to come across 1 decade and down 2 decade, or 40 degrees, which is going to take me, let's see, that would be 20, and 40 would be about in here. And so I'm going to be heading down here like this. Okay, is going to be the slope. Now, in this case, I'm going to run into my second pole, actually my second 0, pretty fast. It's at 10. And so here at 10, I'm going to have a pole which is going to shift me up 20 dB per decade. And so here at 10, where I cross 10 here, I'm going to go from a minus 40 dB per decade to minus 20 dB per decade. So I'm going to go across and down about here, and my slope of my line past this point is going to go like this. Okay, so this is going to be minus 20 dB per decade. Got a little chunk in here that is minus 40 dB per decade. Okay. So that would be our magnitude plot for this, kind of. Okay, now here's where we really kind of got to think through this. If we go back to our rules and look a little bit further in here, we've actually got some other stuff going on here. It doesn't always break real clean, depending on whether it's overdamped or underdamped. It may have an oscillation at that point, which will create a significant change in magnitude, the magnitude ratio. So in this case, what we've got, if we go back and calculate our omega n, and we know that 2 zeta omega n is equal to 3, and so our zeta is going to be equal to 3 divided by 2 omega n, and this is going to be 3 divided by 2 square root of 50, and I worked that out, and it comes out to be 0.212 for our zeta. Okay, so look back at our plot here, and we can see that we're about 0.212, and so what we're going to end up doing is we're going to actually have a little bit of a resonance there, and before we drop off and follow our line down. So it's going to come up, and then it's going to go down like this with a 0.2. If we had a very light resonance, it would go up and then down, and you notice that the scale on here is 20 dB for that peak. And if it's heavily damped, zeta at 0.9, then it just kind of rolls through like we would expect almost a first order system. Same way with the phase. Here with our case at 0.2, we end up breaking pretty quickly through here, and as we go through here, go through that resonance, and it happens fairly abruptly. We get the phase change on that. Okay, so whenever we do a second order system, we've got to kind of squint our eyes and sketch in this. Now, my personal thought on this is kind of three. I've always liked three settings, and so heavily damped goes like this, lightly damped goes like this, and somewhere in the middle goes kind of like this. Okay, and if you do that on your homework and on your exams, that will be adequate for the sketching of this system. Okay, so let's go back to our system, and we've got a medium damped system, a 0.2, and so we're going to go up about 10 dB, and so that puts us about in here. So our peak is actually going to kind of roll up like this, and then down here, something like that. Okay, and our peak should happen at that resonance in there. So something like that would be what the real system would look like on there. Now let's look at the asymptotic phase in here, and of course by this time we should be getting pretty good at this. We've got 0, 90, minus 90, minus 180, and we start off with a phase of 0 because our slope is at 0, and 0 out here to 7, and so we're out here somewhere. And then we get a shift to minus 40 dB per decade here for a little bit of frequency, and so that's going to take us down to minus 180, which is down here, and then we're back to minus 90 out here at 10. And so we go to something like this. Okay. Now, this first one, the second order system, is going to transition fairly quickly, and so we might sketch it in something like this, but about the time we get it heading down, we're going to be heading back up again, so it's going to go like that. Would be a reasonable sketch for that second order system. Now, if we have a second order system in as two zeros, two complex zeros, it's all just inverted from what the poles are, as we can see here. So that's how we would handle a second order system for sketching on the Bode, just like that. Okay.